So let's start off by looking at a vector function. So if we draw out three axes, we'll call that our y, our x, and our z. Then in a vector function, every single point will have associated with it a vector. So let's say, for example, we're looking at fluid flow, then we could say that that point there will have a vector associated with it. The direction of the vector would be the direction of say a molecule of a liquid, and the length of the vector would be the velocity of that molecule at that point. So let's imagine we picked other points and we could draw out a vector function. Okay, so that just represents the fluid flowing at all different points. So we could write that the vector function f is a function of the position x, y, and z. Now we can split that into its components. So you could say that if you take in the x direction and call that a vector I, so it's a vector I of length 1, so that's a component vector of length 1, and j would be in the y direction and our k would be in the z direction. So these vectors here can be written as the summation of multiples of these component vectors. So we can then write it out as the vector function of x, y, and z is equal to the component vector I, which will give you the function in terms of the x direction over x, y, and z, plus the function j in the y direction over x, y, and z, plus a function over component vector k in the function in the y direction, function in the z direction of x, y, and z. Now, best done by example. So if we were to write out a two-dimensional vector function, say f of x, y, and we let it equal minus I in the y direction plus j in the x direction, all upon the root of x squared plus y squared. Then we can draw that function out. We call that our x and our y. So if we went to say along 1 and up 1, so we're looking for the vector at that point 1, 1. So x is going to equal to 1. So that means it's going to be, this value will be 1. So that'll be 1 in the j direction, which is up here. So that will give you that component there in that direction, which is equivalent to this component here. And then we're going to have the y direction, it's going to be up 1. So the y direction there is going to be value 1. It's going to be 1 in the minus I direction. So that's there as our I. So that there's our minus I. So it's going to be minus 1. Okay, so that's there. That there is in effect this, like this second component here. So the vector, sum of those, is going to be a vector in that direction there, and the length of it is going to be a length of a unit length 1. Okay, and the same will occur if you put the values in for this point here, another point here, and a point down here, point there, there, and there. Okay, so what we're going to do is we're going to build up the vectors that are going to be tangential to a circle. And if you were to come further out here, say along 2 and up 2, you'll find that the value of the magnitude here is still going to be stuck at 1, because we're dividing throughout by this x squared plus y squared. So you just put those values in, and you'll see we'll get the same effect occurring. Okay, so that's an example of a vector valued function, and I've got access to a little M file which I found online, and I'll put a note down below the video and you can go and get it. If you've got MATLAB, then you can use it to draw out any vector valued function, and I've actually drawn this vector valued function in the example just coming up. Now I also have a copy of an Excel file that will allow me to do the same, so I'll go and fish that out and I'll put that in if you don't have access to MATLAB. So I've put a copy of an M file down below where you can use in order to draw out vector fields. I got this online, so I never created it myself. And you can see from the one I've put in, we're drawing the one there that we've just done, the example we've just done, and you can see the vector field in 3D. Now, this is a course on vector calculus, but I was going to introduce it in terms of the electromagnetics, because a lot of the stuff in vector calculus was either derived directly or was applied to the area of electromagnetics. Now I'll go through, and this first video here is really going to be a kind of crash course on electrostatics, and it's just to give us a kind of lead in. It's, as the channel is meant to be applied maths, so we're going to not just do vector calculus as a mathematical thing. We're going to do it and we're going to apply it to the ideas of electromagnetics. So first of all, we're going to have a wee look and we'll see what we're actually talking about. We're actually talking about an electric force. So if you just watched the little video, I made that little video just showing my examples of electric force. Okay, so you can watch that now. So if you rub a comb against your hair and bring it against the water, you'll see it bend in the water. So it's applying a force on that water, some kind of electric force. Okay, and also you can see it whenever it picks up little pieces of paper. So I hope that little video has convinced you that there is actually something happening, something worth looking at. Now, we've seen then that there is such a thing as a force, and we can call it for the moment just an electric force. And by experiment it was shown that this force is not only attractive but can also be repulsive. So I could get different material and put it next to the water. Instead of attracting the water, it would repel it. So Benjamin Franklin, he came up with the idea of the electricity being of two types, either a positive type or a negative type, and this positive negative would describe the attraction and the repulsion. So he also came up with the idea of a single fluid model, and the idea about this is that all matter has something, so for at the moment we can just call it a fluid, and either it can have a deficit of that fluid or an excess of that fluid. But what is this fluid that we talk about? Well, the fluid that we talk about, we give it a name, we call it the charge. So there's only really three things that we're interested in here as far as the charge is concerned in this course. We know that like charges will repel and unlike charges will attract. So two positive charges will repel, two negative charges will repel, and a positive and a negative charge will attract. And you can work out the force of attraction or repulsion using Coulomb's law, and we've just simply written Coulomb's law out here. So that's really just reading, saying that there's a force here that's the force on 1 due to 2. Now 1 is just the charge Q1 and 2 is the charge Q2. So we're saying the force on Q1 due to Q2 is equal to some constant times the magnitude of the charges Q1 and 2 multiplied together divided by the distance between the two charges squared, and that force is in a direction along the line joining them. So it'll either be a charge which will be in one direction or another direction but along that line joining them. So let's say, for example, so you can see that R12 there. If we had a charge Q2 and a charge Q1, then we could see if we had an origin there, then the vector from O to Q2 can be written as R2, and the vector from O to Q1 can be written as R1. So that R12 would just be R1 minus R2, which would give us a vector pointing in this direction. You can convince yourself of that. So it's going to be that vector in that direction plus a vector in the negative sense of that direction. So that'll give us a vector in this direction, which is this vector here, R12. Now, there's one other thing that we're interested in, and that's the idea of superposition. So if we were to then bring in, say, another lot of charges, so they're in blue there, a few other charges, then what we can do is we can work out the charge on 1 due to 2, and we can work out, the force on 1 due to 2, we can work out the force on 1 due to this one, and this one, and this one, and then we can add up those forces vectorially, and we can get the final force that Q1 would experience due to these other charges. So Coulomb's law in itself assumes instantaneous interactions at a distance. Now, what do I mean by that? Well, the force that Q1 experiences due to Q2 is dependent on how far they are away. So let's say I moved Q2 further away, then according to Coulomb's law, instantaneously the force will change. But that's not the way nature works. And the Michael Faraday came along and he was doing experiments, and he came up with the idea of an electric field. So what Faraday noted was that a charge will change the space round about the charge, and there's another charge there that changes the space round about that charge. And then what we can do is we can say, well, if we were to have a multitude of charges, so there's the charge there and there, all the blue ones, and we'll notice that we'll have some kind of field lines round about those charges. So the further away you get from the charge, the less force of attraction or repulsion you'll experience, dependent on the inverse square law. So what we can do then is we can use superposition, and we can add up all of these fields, okay, for each individual charge and create one overall field. And then we'll note then that this is not the only distribution of charges that could create that field. You could come up with a variety of different charge distributions, but you would still come up with the same field. So it means that this field then here is really independent of all of these charges. So then what we can do is you can say, well, let's take some unit charge and we can position it at lots of different points in this field. Okay, so you can take this and you can position it lots of different points all over the field, and then you can measure the force on that unit charge. So that's in effect what we've done down here. We've imagined putting a unit charge on each of the points here, and we measure the force on each of those unit charges. Okay, so then it means that the idea of instantaneous interaction at distance has been kind of split into two. We've thought about the charge creating a field, and then another charge coming into that field and experiencing a force. So this charge here that comes into that field, it doesn't matter where these other charges are. Okay, it doesn't care about these other charges. All it experiences is a field, and as I say, lots of different charge distributions could create that same field. So this point here, this point charge, has got no knowledge of the position of any of these. So we could bring a distribution of charges, say that's the pink ones there, into this field, and then we can work out the force on each of the charges is going to be given by the electric field strength, which is just a function of position, times the value of each charge. So electromagnetic theory is derived in terms of electric and magnetic fields, and the effects that these fields have on charges and moving charges or currents. And these moving charges and currents are the actual things that created magnetic fields in the first place. So that concludes the briefest of introductions to electrostatics. Now the reason for going through that really is because a lot of the rest of the work that we're going to do is focused on answering one of the questions. The question being, what is the electric field given some random distribution of charges? So it's really this problem up here. We have the overall electric field given by some random distribution of charges. So I'll get you on the next video. Goodbye.